All right, everyone, my name is Han, and today I'm going to talk about reformers, which is a short for reversible transformer. It is an optimized version of the famous transformer from Attention is All You Need paper from 2017. And Pooja, this is for you. So before we dive deep into reformer, here is the model architecture for transformer. So the transformer, this is the base architecture used by many state-of-the-art models such as BERT, GPT-2, XLNet, etc. So transformer follows the similar encoder-decoder architecture for neural language models. So on the left-hand side, here we have the encoder, and it takes a positionally encoded input embeddings and pass it through multi-head attention layer, and then go through a feed-forward network. And the output is used for the decoder part together with the expected or your trained data set, shifted one to the right or however many units to the right, and go through the decoder part, and you will learn the output probabilities of what orders they would expect. So usually the default transformer is stacked here, and is 6 times. So there's 6 repeating modules of this, and the multi-head attention is stacked 8 times. So they can parallel process a lot more information. But there's several problems with the transformer model. The model is notoriously memory intensive and time consuming to train. So for example, when I implemented a transformer for the Berkeley CS128 assignment, I could only use a batch size of 48 for a very small vocab size of only 10,000 words. Before get TensorFlow throw me like memory out of bounds, not enough memory errors. And the 2 primary reasons is that transformers, there are 2 primary reasons for the memory intensiveness. So first is this multi-head attention part, and the second one is during the feed-forward network part. So that's the how the reformer authors apply computer science skills or computer science discipline into deep learning. So transformer, it uses a scale dot attention to find the best value for a query. So here, I don't think this is quite right because I don't think this is a dot attention. It doesn't look like a dot attention, but using my non-academic interpretation, the bigger the value of it, so usually when people do dot attention, you have 2 vectors, and the bigger the value of the dot product, the closer the 2 vectors are together, right? So basically you're trying to find the best vector for the best value for the query that you inputted. So which means that dot product attention is trying to look up the embedding that has the highest value given the input. So in terms of computer science, let's think in terms of a huge lookup table that you have. Give it a query, and the dot, you go through every single one, and you find the best value out of the big lookup table, right? So that's how memory works. So so now, as with all the, I guess, LeetCode or computer science interviews, after you have an algorithm, you have to do a complexity analysis. So what's the complexity of using of the transformer model? So in the paper, they outline basically this part is the equation for the scale dot product attention. Scale dot attention. So this one is sort of, you can ignore that because that's just a dimension of the K. But so here you have Q of length L, and you have multiplied by the K. So this is Q vector, and this is K vector. Both are length L. you get a big fat matrix. So your space complexity is your length squared, and your time complexity is also length squared. So in the paper, they provided an example that a sequence length of 64K is going to produce a 64,000 by 64,000 matrix at 32 bits. That's going to be 16 gig of memory. So obviously that is why it is very memory intensive to train. But since this is essentially a lookup table, the reformer authors try to approach this using a hashtag, a specialty hashing mechanism to solve this problem or to reduce the complexity. So in the paper, it has this fancy diagram talking about how they use locality sensitive hashing with chunking and sorting to reduce the complexity of the dot product attention. It's all in the paper, but since this is, I guess, my presentation, so I will provide my own interpretation. So for example, here we have 4 vectors, V1, V0, 1, 2, 3, and we have 4 buckets, right? So let's take the first 2-bit as their locality or how close they are. So 1, 1 will go here, this one goes here, 0, 1, 1, 0 goes here, and 0, 0 goes here. So here you have V1, V3, and then here you have V0, and in the 0, 0 bucket you have V2. So that's how you sort or how you hash things into different buckets using locality sensitive hashing. And with this, you might notice right away that there's a problem. The bucket size is imbalanced, right? Because you have 2 here, 1, 0, and 1 here. So how do you solve that? You use chunking. So basically, you chunk to make sure every bucket are the same size. So sometimes you have overflow from other buckets to from a previous bucket to the next one. And that is going to help the algorithm solve the problem. And chunking might sound pretty fancy. And in reality, if you look at the code, this is directly from the reformer code, it is basically just reshaping. It's just a reshaping function to make sure they are the same size. And so since this is a language model, so how do we compare how close they are together? So previously I mentioned that when you want to compare 2 vectors, how close they are together, you take a dot product, right? You want to find the smallest angle cosine similarity between the 2 vectors. So they have this fancy diagram. But here I'm going to draw it out as to how I understand it. So basically, if you can think, you can try to think of like all the word vectors you have here, all the vectors you have here. Right? You have a lot of vectors, and basically what they do is they just throw through 2 lines, and they put, this is a bucket 1, this is bucket 2, bucket 3, and this is bucket 4. This is why they want to, this is the reason why they use an angular locality sensitive hashing, because usually in deep learning, we use cosine distances to measure how close they are together for this angle, right? Because you want this angle to be small, so the vectors are closer together. And they do this multiple times, so they can achieve the best separation between all the vectors. So they sample the rotation. That's where this goes. They do a random rotation, sample that, random rotation, sample that, and random rotation, sample that to make sure they get the best separation of different vectors and get the best bucket size, etc. And the code is actually not in the reformer repo, but in Tracks Layers Research. And since everyone is staying at home, they have two versions of the locality sensitive hashing. So here on the right, there is some sample rotation code. Everyone stay at home, so feel free to read the code and knock yourself out from here. And so what does it help? How much does it help? So basically, so this is the equation they have on the paper, but in summary, it reduced the time and space complexity from O(n) squared, because you have two big things multiplied together, into n log n, because now you are searching for very specific, for much smaller buckets. So that's going to shrink down the size of your search by quite a lot. And now let's look at the second pain point of the transformer model, which is the caching at the feed-forward network. So we call in like plain vanilla affine layers. We used some dynamic programming and caching techniques to store the activations for the backward pass to make it calculate faster. So the author used an idea that came from a paper called Reversible Residual Network, which is published in 2017. In that paper, the authors designed a network which activation caching is no longer required. So basically, a reversible net uses two inputs and two outputs instead of just one single input and one single output, and they zigzag. And so the backward path is going to be a lot faster and a lot more simple to calculate. And here is a short snippet from the reformer code. So here you can see they duplicate the input, they swap it, and they get the output. And this part is the actual the highway layers. So they have a block called pre-attention, a block called attention, and block called post-attention. Oh, I'm running out of space. And you go through here, 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 and then you go here, and then you add together at the end. So that is how this is how they rotate, and they just flip-flop the things on the backward pass during training phase. So overall, the time complexity analysis from before and after is laid out in the paper as this. But I mean, it's really quite, it looks quite complex, but the only thing, well, not the only thing, but the most important thing you can note is here. You have a square term right here. And that got reduced to the number of chunks in the locality sensitive hashing, the trick they use. So overall, it goes from O(n) squared to O log n. So in summary, the key takeaway for this presentation is transformers, O(n) squared, reformer, O(n) log n. So it reduces the time complexity and space complexity, so you can fit a much bigger network in a set amount when you are memory constrained. It's linear, it's faster, and it supports either longer input sequences or longer vocab size. And in the paper, so for transformer, usually the max input token size, token length is 512. And in the paper, they said something like 64,000, but I'm not 100% sure about if that is a valid comparison, but so don't quote me on that. But it gives you a lot more work space in the memory. And they achieve it using first, angular locality sensitive caching. And second, it uses reversible net on the feed-forward network part, on the highway pass around. And best of all, everything is written in tracks. It is yet another research-oriented deep learning library that doesn't read the same as TensorFlow or PyTorch. So yep, I'm not sure why they want to torture like normal people with yet another research-oriented code and library, but that's that. So here are the references. The first is the Reformer paper. The second one is Attention is All You Need. And the third one is the Reversible Residual Network paper. And of course, there's always the J. Alamar blog, which is awesome. It's graphical, it's interactive. And any questions?
All right, so our first question is from Mani. So Mani asked, why would cosine distance be used instead of the Euclidean distance?
The cosine distance is easy to calculate, right? It's really fast and easy to calculate the dot product of two matrices, and you want to get how close they are together. You want to get the angle, how close they are together in the of the two vectors, not the Manhattan or the Euclidean distance of the two vectors. That's usually the case for language models. So like one of the good example is when people showcase the simple work-to-vec model, you have king and queen is similar to man and woman, something like that. That is measured by cosine distance of the two word vectors. So there's a lot of research built on top of that. So that's how that propagates through.
Great. And another question. Well, first, yeah, another question from Mani. You mentioned compression. Can you elaborate on it?
Compression. I don't recall.
Okay, maybe yeah, Mani, if you could clarify that a little bit more in the Q&A. While we're waiting for that, there's a question from Krisha. When putting the vectors in the hash buckets, why do we only consider the first 2 bits?
Oh, right. So this one is this slide is not particular. It's not particular to how reformers perform. This slide is just to help help me understand how locality sensitive hashing works, right? Because I want to showcase how you use certain measures. In this case, we're using the same thing, putting in the different buckets, right? But in reality, for reformers, they use this because everything is so every word has its in an event, or every word is a vector, or every token is a vector, and you want to compare, right? So that's why in reformers they slash 2 lines, and then they so you have a lot of vectors in the space, and you have 2 hyperplanes just through Ninja and separate them into different quadrants, and you put different quadrant into a bucket over and over until it's a lot more balanced across different buckets. So it's not particular the first 2 bits. So it was just to demonstrate the idea of LSH.
Okay, I'm not seeing any additional questions. So I'll just say on the point about measuring angles, there's actually some really interesting work about how vectors in high-dimensional spaces measured with cosine similarity essentially can be used to do representation of semantic concepts, and in fact, even to do Turing-complete computation. So I'll send a quick little link to the chat that gives a little bit of the background on that idea. It's older than the idea of these transformer networks and sort of key query networks, but it's really done quite well with these new architectures.
Yes, Charles is the expert in all this thing. I am just a pleb trying to understand what people do in different conferences, trying to read the papers and explain it in my own words.
Thank you, Han. That was really, really good. I just want to add a note. We're going to drop all of the slides that the speakers are using because I saw like your slide had a lot of really interesting links. So we will drop it in the WNB Slack community. I just posted the link for that again in the chat.